Hello, this is Ms. Billerbeck, and we're going to talk about 17.3 independent events. So, two events are said to be independent events if the occurrences or non occurrence of one event does not affect the probability of the occurrence of the other event. For instance, rain in Spain has no effect on fish being caught. Also, the number of seeds in an apple have no effect on the number of cherry blossoms in a tree. So these would be independent events. They have no effect on the other event. So let's look at if A and B are independent events, the probability of both events, A and B, occurring is the product of their individual probabilities. So if we have the probability of A and B happening, then we multiply the probability that event A will occur times the probability that event B will occur. So here's an example. So a letter is selected at random from each of the words bread and butter. So first we want to look at the probability of a vowel in bread. So overall there are 5 letters. So we're going to put a 5 down below for our sample space. But there are 2 vowels. So that's the probability that there's a vowel in bread. Now a vowel in butter. So butter has 1, 2, 3, 4, 5, 6 letters. So its sample space is 6. And it has 1 vowel and 2 vowels. So here are vowels as opposed to these 2 vowels. So we have 2 out of 6, which is 1/3. So the probability that they're both vowels will be 2, that a vowel will occur in bread and a vowel will occur in butter is 2/5 times 1/3, which is 2 out of 15 times. So this again is the probability of bread, the bread vowels and butter vowels. Okay, so that's what this one is. So there's an and there. So when we see an and, we multiply. That's very important. Ors we add, ands we multiply. All right, so now we have Sarah and Ryan. And they work independently on a problem. The probabilities that the problem can be solved by Anna, whoops, I switched names, didn't I? So we're going to do Anna here. Or Ryan are 2/3 and 4/7 respectively. This word respectively means the first number goes with Anna. The second number goes with Ryan. So when we see this word respectively, that's what it means. So whatever comes first goes with the first person listed. Whatever comes second goes with the second person listed. So that's the magic of the word respectfully. Or respectively, sorry, not respectfully, respectively. All right, so the probability of A and R. So if it's an and, we have 2/3 times 4/7. So when we multiply across, that's 8 out of 21. The probability of not Ryan. So Ryan was 4/7, so that's 1 minus 4/7 is 3/7. Okay, the probability of not Anna. So that's 1 minus 2/3, would mean that's 1/3. So the probability of A, not R. So we want to multiply the probability of A. So Anna was 2/3 times not R, which is 3/7. So that becomes, we can cancel these 3's out, and that becomes 2/7. The probability that it's Ryan, so we were given the probability of Ryan here, and this is the probability of Anna. Okay, so the probability of Ryan is 4/7 times the probability of not Anna, which is 1/3. And we multiply this across, and we have 4 out of 21. All right. So I wish we were done, but we're not quite. We still have a little more to go on this. So it asks us a difficult question. It asks, what's the probability of A and not R, or A and not, or R and not A? So this was an or, so that's a plus. The A's are times. Okay, we already figured out A and not R. A and not R was 2/7. So this would be 2/7, and we have an or, so plus, and then we found R and not A. So that's 4/21. Okay, so we need a common denominator. So 3 times 7 gives you a 21. So this is 6 21s plus 4 21s gives us 10 21s. So this one's 2 times 5, this one's 3 times 7. There's no way to get that any smaller, so that's our answer. All right, that was a lot of work to answer that question. All right, so what this means, but by the way, is we have, this is the probability that Anna or Ryan wins. Okay, or solves the problem. Okay, so that's why it was so difficult, because only one of them solved the problem. All right, so let's go to example 3. So example 3, the probability that a certain MP3 player fails within 1 year of purchase is 0.15. Ms. Fay buys 3 of these MP3 players. So what's the probability all 3 fail in 1 year? Well, let's look at the probability tree. All right, so this is a fail, fail, fail. So if we multiply, if this fails and this fails and this fails, so that means we're multiplying, then we're going to multiply 0.15 times 0.15 times 0.15. I ran out of space. I would have said 0.15. Oh, I'm getting tongue-tied. So that's this actually equals 0.15 cubed. We can use the exponents if there's 3 of them multiplying. So we use an exponent, and this is a very unlikely situation. So if we look at the percent of this happening, we move this over 2 spots. Okay, the percentage that this would happen would be 0.34%. Okay, that is not very much. That's a very small probability that all 3 would fail. So she's being very wise to get 3, so at least she has one of them working. So then we look at the probability that at least one fails in 1 year. Well, that's going to be hard. I mean, look at this. We have to go down all these paths. So these are nothing fails. This is, oh, there's a failure right there. Ooh, we have a failure there, so that's out. And then we can't even go this way because that's starting out with a failure. So the only way we can go is that way with no failures. So what we want to do is we're going to do 1 minus the probability of none failing because everything else has at least 1 failure. So we have 1 minus, and the probability of none failing is 0.8 times 0.8 times 0.8. So we know that 0.85 times 0.85 times 0.85 is now 1 minus 0.85 cubed using an exponent. Okay, so I am going to use a calculator for that one. So 0.85 to cubed is 1 minus 0.614. Okay, so when we add a 1, subtract, whoops. There we go. All right, so when we do 1 minus, we get 0.386. All right, so if we look at this and we move it over 2 spots like that, that means it's 38.6% likely that at least one will fail in 1 year. So that's pretty interesting. All right, so that's how you would figure that out. And this is how you would do the tree, by the way. You didn't notice. So this is the failure, this is the success, where it didn't fail. Then the next opportunity over here is we have failure, success. Then the next opportunity, failure, success, failure. So this was success, failure. This one's success, failure. And then when we go down the failure tree, we could get it repaired, I guess. But then we would have success, failure. Then we'd have to get it repaired again, and then success, failure. And then here we'd have success or failure. All right. So this is kind of a sketchy branch because you do have to repair it if it's failed to be able to keep going. There's some logic to that. All right. Well, you have a lovely day.